Okay, so we're going to start 9.4, a lesson on polar equations of conics. And so when we're thinking of polar equations, or conics, we're thinking ellipses, circles, parabolas, hyperbolas, and we have a picture of those down here. When we're working in polar equations, the eccentricity is going to be important for us. And so remember that eccentricity was C over A, and that's how we got that. And that determined whether it was maybe more circular or elongated for an ellipse, or for a parabola or hyperbola, it would determine like whether it was how much curve there was or how straight it was. And so for an ellipse, we would have an eccentricity between 0 and 1. For a parabola, it has a eccentricity of 1. And for a hyperbola, it has eccentricity greater than 1. And then these down here are the rectangular equations for each of those, if you can remember that. And so in this case, it's the very basic where the center is 0, 0, or in the case of the parabola, the vertex is 0, 0. We're going to refer back to this chart with eccentricity quite a bit in this lesson, so because we need that to determine what kind of equation we have. All right, so if I scroll down a little bit, I have, it's talking about the forms, the polar forms of the equation of a conic. And so a conic section with eccentricity greater than 0, and D, which is going to represent our directrix, is greater than 0, and the focus at the pole has the polar equation, blah. So basically what we're going to do is we're going to maybe be given a directrix and the eccentricity, and we'll refer back to this. The equation, regardless of ellipse, parabola, hyperbola, is going to be one of these forms. So R equals ED over, in this case, 1 plus E cosine theta. So E is your eccentricity and D is your directrix, wherever that's going to go. We talked mostly about directrix when we did parabolas, and so for a parabola, just kind of a review there, is maybe we had a vertex here and we had a focus, and that distance, whatever that might have been, let's say that was 2 units from the vertex to the focus, then on the other side, we would be 2 units away from the vertex, and there would be a directrix, okay? And so that's what we're determining as far as directrix goes. And we have examples down here at the bottom of having a directrix with our parabolas. But again, our equations, types of equations or forms of the equations are not going to change dependent upon what kind of conic we have. So depending on where our directrix is, so in this case we have x equals d, let's just, d is positive here, then we're going to have this form of the equation. In turn, down here, if we have a y equals negative d, then our equation is going to be in this form. So we need to pay attention to what our directrix is to determine the form of the equation that we want. So you can see that for each one of these, even though we have parabolas for all of these, the same concept would work for hyperbola or ellipse. So this center here, that's the pole in our polar equation, okay, or our polar coordinate system. If the directrix is aligned to the right of the pole, then we know that our directrix is going to be x equals d, which means we would use the form of this equation. In the second one, so we're over here, I see that my directrix is to the left of the pole, which gives me a directrix x equals negative d. So I would go up to my table here, or my chart, and when x is negative d, then the denominator is 1 minus e cosine theta. In the third picture, I have my pole, and the directrix is above that. And so I get an equation y equals d, and then when y equals d, our equation is r equals ed over 1 plus e sine theta. And then in the fourth picture, we have our pole and the directrix is below that, which gives us an equation of y equals negative d, which is our last form of the polar equation for a conic. And so that's what we're going to refer to. All right, so in the first one, it says determine the eccentricity, the type of conic, and equation of the directrix for each polar. We got to do a little bit of work with this one because the form of my equation at top with a plus cosine is r equals ed over 1 plus e cosine theta. And so you'll notice that we have a 1 here, but we don't have a 1 here. So I'm going to have to adjust my equation to make this work for me. So I'm going to come over here. This is just a little arrow. And in the denominator, I'm going to factor out a 3, which is going to give me my 1. And then I have 2.25 divided by 3. So I'm going to factor that out, which gives me 0.75. So you can see that now the denominator is starting to look like that 1 plus e cosine theta. And then my numerator is still 9. Well, this is just basic algebra now. I should be able to reduce the 3 and the 9, which gives me 3. So now I have 3 over 1 plus 0.75 cosine theta. So that e is 0.75. That's my e. Now the numerator is how I'm going to determine what my d is, because remember the numerator is e times d. So e times d in this case is going to be 3. Well, if e is 0.75, I'm going to take 0.75 times d equals 3. And so we're going to divide by 0.75. 3 divided by 0.75 is 4. Okay, so that means that our d has to be 4 in order to get our 3. Okay, so this is our reduced form of the equation. But using that, we find out that our e is 0.75 and our d is 4. So it says determine the eccentricity. So we did that, 0.75. What's the type of conic? If I go back up to my note, the top of my notes here, my eccentricity is 0.75, which is then between 0 and 1, which means I would have an ellipse. So it's an ellipse. And the equation for the directrix well, this had a plus cosine in it. So if I go up here, this form, that very first form, had the plus cosine, which gives me a directrix, a vertical line of x equals d. So that's what I want to use. X equals, and my d was 4. So there's my directrix. So really, my answers are the eccentricity is 0.75, it is an ellipse, and the equation for the directrix is x equals 4. So I'm constantly going back up to that chart. Now, if you were like, well, I really don't know what this is, and you wanted to graph this, this is a good opportunity to see let's see if we can open these both up. Like I said, this is a good opportunity to see what the graph looks like. So I'm going to go to my y equals, and I'm going to clear this out because I had a different graph on there from our other example. I'm going to check my mode again, make sure, so I'm in degree mode. Let's get out of that. I want to check, actually I want to check my window. And looks like I'm pretty good there. We'll go down to our x. So again, if we wanted, well, let's take our steps because this is going from 0 to 2 pi. Let's go pi over 12, which will get us all of our values that we want. Hit the right button, pi divided by 12. And that will give us, even though it will give us some extra values, it will also give us our 30, 60, 45s, all of those. And then let's make our max and min 10 and 10 again. Negative 10 to 10 for our x, and then we'll keep our 10 to 10 for our y, and then that'll make our make it a little more square. Okay, so we go to the y equals, which is really r equals in polar form. And if you remember a little trick before, we can make a fraction if we hit alpha and y equals, and that's going to give us an option of how we want to enter our fraction. So I'm going to pick number 1 there, and that's just going to give us a numerator right over the denominator, and we don't have to use so many parentheses then. So the original equation is 9 and then over 3 plus 2.25 cosine theta. And we can graph that. And there's our ellipse. Now, if we wanted to see a little bit more, we could change our. Well, first of all, let's go to zoom and square this thing up. So number 5 there. And then I'm going to change my window. Well, actually, I don't even have to change my window. There's my ellipse right there. That's a good one. But we can change the window if we would like and have a little less of the positive and a little more of the negative. So maybe we wanted to change the x max to, I don't know, let's say 6. And then we graph it. Kind of centers it up a little bit more there. But there's our equation. You can see that, yes, it is an ellipse. It's a little jagged because, well, it's our calculator and maybe our lines wouldn't be as smooth there. But that's our equation. Okay, and then in the next problem, if we wanted to go ahead and graph it, we could, just to take a look at it since we've got our graphing calculator out. So I'm going to clear this first equation out, and we have negative, we want to make our fraction bar. There we go. And we have negative 16 over 4 sine theta minus 2. Okay, so you're right. Hopefully you can see what's happening here, but I'm going to, again, change our graph just a little bit because I have the center of my graph in the middle. So I am going to